So we are very happy to have Tanya Roussy here. She's a graduate student in Eric Cornell's group. And she's exactly doing what we are doing too, and that is building extremely cool experiments and using them to exclude dark matter. So we are very happy to have you, and please go ahead and give us your talk.
All right, thank you so much for inviting me. So like we just said, today I'm going to talk about an electron electric dipole moment search and how we use that to look for dark matter. But before we really get started, just to make sure we're all on the same page, I'm actually going to start this talk with a brief introduction to particle physics. So I am an AMO experimentalist. I'm not good at math. This is not my area of expertise. So please bear with me.
Good.
So here's your average high energy theorist, and they are enjoying how awesome the Standard Model is. So it really is one of the crown jewels of modern physics. Virtually every time we test it, the model's predictions agree with experiment to remarkable precision. Except it's not always right. And when it's wrong, it's really wrong. For example, the Standard Model fails to explain the baryon asymmetry, or in other words, why there's matter in the universe. There's other problems like dark matter, dark energy, and the whole issue of quantum gravity, but the fact that it fails to explain why we're all here is really problematic. It turns out that the problem with the Standard Model is that it's too symmetric. It needs some more symmetry violation, and in particular CP violation, to explain things as fundamental as us. So theorists have been busy creating new models to explain our existence, and those new models have the extra symmetry violation we need. But the catch is that they don't know exactly where to put that symmetry violation. So that's where experiments like ours come to the rescue. Measurements of the symmetry of fundamental particles like electrons can help point new physics theories in the right direction. That's why we are measuring the electron's electric dipole moment. Every measurement that we and other teams make helps to constrain new physics theories by kind of narrowing a really big parameter space. Okay, so that's the history of particle physics. So just to make it clear, I want us all to think about why an electron electric dipole moment would violate CP symmetry in case some of you aren't familiar with this. So here's a little cartoon I made of the electron where I've indicated the electric dipole moment as kind of an oblong shape with positive and negative poles. I've also indicated the spin in the normal way plus a little swirly bit just to make it really clear. And you can see that when we reverse the arrow of time, the spin will flip, but the Edm doesn't. So assuming CPT is conserved, this means an electron Edm also violates CP symmetry. So this cartoon is to show you the status of the field. First of all, the axis is in units of electron charge times centimeters, which is super weird and not intuitive. What I want you to understand is that the electron Edm is really small. It's so small that our current precision is like if the Earth was spherical, we can measure its roundness up to adding or subtracting like a coating on the entire northern hemisphere of some kind of virus. I won't say which kind. The point is that it's incredibly small and our measurements are really precise. So in this cartoon, you're looking at like basically a timeline of the leading measurements. They're exclusions at the 90% confidence level, which means that each of these measurements excluded an electron Edm up to their uncertainty. They exclude an Edm larger than their uncertainty. Most of the new physics theories predict electron Edms right in the range that we can measure, so our measurements really do constrain these new theories. The Standard Model is orders of magnitude below, so that also means that we have a background-free measurement, or in other words, that if we measure something here, it will very genuinely be new physics. There won't really be any debate. So you can see that all these measurements are done in molecules, which is neat. But more importantly, if you look at the scale here, you can see that we've constrained the electron Edm by 2 orders of magnitude in 10 years, which is really impressive for how difficult these measurements are. A high energy theorist actually once told me that neutron EDMs have killed more theories than any other experiment. And I hope that electron EDMs can move in that direction one day too. But jokes aside, I do want to just belabor this point a little bit more. EDMs are an incredibly powerful probe of new physics. The current leading measurement done by the ACME collaboration actually constrains symmetry violating physics at the 30 tera electron volt level, which exceeds the reach of the Large Hadron Collider. So that's amazing to do something like that in a small lab with just a few optical tables and a vacuum chamber. Okay, so hopefully I've convinced you these measurements are important. The question I want to answer now is, how do you measure an electron EDM? We know it's really tiny, so we have to be careful. So let's just start by imagining a simple spin flip measurement. We can measure this in the presence of some magnetic field, and we'll get some energy splitting. So now add in the effect of the electron EDM. Imagine it's pointing in the same direction as the spin, so the ket represents both the direction of the spin and the EDM. So if you measure that with an electric field pointing this way, the levels will move apart. If you flip the electric field, the levels will move together. You can take the difference, cancel out the magnetic term to first order, and actually get a measurement that's directly proportional to the electron EDM. Okay, so the next question is one of sensitivity. So we're basically measuring zero or something that's very, very, very tiny. So we need to be as sensitive as possible. There's three major things you have to consider. The first, the larger the electric field, the larger the splitting. Second, a large count rate will allow us to determine the centers of the peaks with more precision. And finally, a long coherence time will make the lines more narrow. So altogether, our sensitivity will scale like 1 over the electric field, the coherence time, and the square root of the counts. So because the EDM is so incredibly tiny, to make any measurement worthwhile, you really have to maximize all of these parameters. So to start with, you want the electron to experience a really enormous electric field. And that's why all leading electron EDM measurements are done in paramagnetic polar molecules. An unpaired electron spin will experience a massively enhanced electric field inside of a polarized molecule. The beauty is that this only requires small lab fields to produce. So in our lab with 50 volts per centimeter, we can get an effective electric field of 20 gigavolts per centimeter. That's like a factor of 1 billion enhancement, which is really awesome. But of course, it comes with a catch. So everyone here knows that molecules are more complicated than atoms. As you know, for every electronic state, there's vibrational states. For each of those, there's rotational states. Then you add in hyperfine splitting and Zeeman sublevels and so on, and you can end up with kind of a giant mess. So this can be both a blessing and a curse. It's a blessing because we actually exploit certain molecular states to do our measurement, but it's a curse because it makes the vast majority of molecules that would be sensitive to an electron EDM incredibly difficult to trap and cool. So for this reason, until recently, all molecular EDM experiments were done with a molecular beam. That means that there's a beam of molecules that are literally flying through the lab. They're being read out and prepared in a few milliseconds. So the beam people are really stuck. They can't improve the coherence time unless they make a really, really, really long lab. So they are stuck with improving the count rate, and they've been like amazingly successful with that. But if you wanted to increase the coherence time, you have to be able to trap your molecules and polarize them. So there's definitely lots of groups that are working on the technology to do this with neutral molecules as we speak. And if they can trap their molecules, then they can very easily polarize them. But Eric had a completely different idea, and that was to work with molecular ions, which are super easy to trap. But of course, that's the easy part. And the reason no one else uses ions is how you polarize them while keeping them trapped. So just to make it really clear, if you apply a static electric field to polarize a bunch of trapped ions, you won't be able to keep them trapped. So Eric's insight was to apply a rotating field and to do our spectroscopy in the rotating frame. So with this scheme, we have coherence times that are 3 orders of magnitude larger than beam experiments. It's a really brilliant idea, and we're still the only people in the world using rotating fields to polarize trapped ions. As always, this comes with another catch, but luckily it's not that bad. you have to apply, or we want to apply a bias magnetic field, but we want to apply a bias magnetic field to rotating ions. So the answer is actually to use a quadrupole magnetic field gradient. The ions are driven in uniform circular motion by the electric field. And if you add in the quadrupole magnetic field gradient, these circular orbits have the effect in the molecular frame of having a magnetic field that's aligned with the quantization axis. So the primary component of the spin precession frequency that we will measure is due to this so-called rotating magnetic field. You might ask, why do we need a bias magnetic field? That might be obvious to you. It's for lots of reasons. One is so we can bias away from an avoided crossing between the levels we measure, and the other is so that we can control the spin precession frequency. Okay, so don't worry about the little details. Now you have polar molecules, they're oriented in an electric field, and they're either aligned or anti-aligned with the field, which we call the lower and the upper doublets. With the addition of a magnetic field, we're ready to measure the energy splitting in each doublet. Because of the beauty of something called omega doubling, which is basically just the relative alignment of the spin, the molecular axis, and the internal field in each doublet, the difference between these two energy levels approximately isolates the bit that's due to the Edm, while effectively allowing us to isolate and reject systematic effects. To kind of imagine it simply, we can simultaneously measure these two things. So if we have noise, we can do a differential measurement between these two levels. This super clever idea was popularized by Dave DeMille, and I believe Dima was around at the time they were developing it. Okay, so we do Ramsey Interferometry. So a measurement of the energy splitting or the spin asymmetry looks like this. If we track the phase for long enough, the two Ramsey fringes will go completely out of phase before going back into phase. It's the frequency difference between these lower and upper doublets that are the heart of our measurement. So the details do not matter for this talk, but preparing and reading out an ornery molecule like hafnium fluoride is no small feat. We manage it with 14 lasers and lots of patience. And as a grad student, the vast majority of my time goes to massaging all these lasers into working for me. If you want to know more details about it, please feel free to ask about it at the end of the talk. So taken together, these are the basic ingredients for our measurement, but there's one more really important thing that we need to remember to do. And that's to blind our measurement. So because the effect we're measuring is so tiny, we need to be careful not to introduce sources of experimenter bias. We have an expectation that our measurement will be zero. Other recent measurements are consistent with zero. But what we don't want to do is keep tweaking our analysis until we get the expected result. So here's like an interesting historical example of why blinding is a good idea. This plot is a temporal record of measurements of the speed of light. And you can see that this series of measurements from about 1930 to 1940 disagrees with the current value by almost 20 kilometers per second. It's been speculated that the experimenters in this period were accidentally biasing their result. They were searching for sources of errors, and they continued to search until they got a result close to the accepted value, which seems to have been set around this time. So this is exactly the kind of problem that we want to avoid. So that's why we collect our data blind. In practice, what this means is we add a randomly generated number to all of our measurements. We do all of our analysis and systematic studies with that number added in. We don't remove the number until we're sure of all of our analysis and we're ready to publish. So this makes things pretty spicy. Like in practice, you have a certain expectation and you literally have to wait years to find out if your result matches it. It's great if you love suspense. Okay. So that is a very broad overview to give you the general sense of our EDM measurement. I'm not going to go into details because I want to spend the rest of the talk introducing you to our dark matter analysis. And I'm going to give you a recipe for doing a dark matter search of your own. But of course, if you're interested, I have like 50 bonus slides, so please feel free to ask about it. Okay. So let's say you have your own precision measurement of something. Your data will basically look something like this, where you've measured some energy splitting a bunch of times. Your measurement probably won't be zero like ours. Now what you'll do is you'll take your measurement, you'll put it in a histogram, do some statistics, and you'll say, whatever you measured is such and such. In our case, we found that up to our uncertainty, the electron is essentially round, or in other words, the magnitude of the permanent electric dipole moment of the electron is below our measurement sensitivity. But all of this analysis is predicated on the assumption that our measurement is a DC quantity. So the cool part is that precision measurements like these can do double duty as dark matter probes, and it's essentially free in the sense that you don't need to take any new data, you just need to reanalyze your old stuff. Often this will translate to looking for an AC signal in your data. Okay, so in our case, it turns out that a cosmic dark matter field would make a parameter in our molecule called CS oscillate in time, which would make the molecular Idiom, which is what we actually measure, oscillate in time. But for a lot of precision AMO experiments, the same general idea will be true. The thing that will change is which dark matter coupling you're sensitive to, and as a result, which parameter in your system oscillates. So in our case, we're sensitive to a broad class of potential dark matter particles called axion-like particles, or ALPs, and I'll probably be using the term ALP interchangeably with dark matter and axion-like particle throughout the talk. So the general task is to examine your data, but as a function of real world time, and to check if there's evidence of a coherent oscillation. So you can almost imagine a wiggle in this data here. With our data set, we were able to constrain the coupling strength over 7 orders of magnitude in axion-like particle mass, and I expect that a lot of precision measurements will have a similar reach. This is one of the big advantages that precision experiments like ours have over things like haloscopes, which generally only exclude a very tiny region in parameter space. So please forgive me a moment of evangelizing here. Like I mentioned on the previous slide, a big advantage of using AMO and precision measurements as dark matter probes is their ability to exclude huge portions of the parameter space at once. When you have 40 orders of magnitude of parameter space, this is really important. But there's a broader point to be made here. So when most of us think about detecting new particles, we think about accelerators. But accelerator energies are likely to remain flat for quite a while to come. So we really need to look outside of the accelerator paradigm to solve pressing problems like dark matter. And of course, there's people who've been doing this for decades already. There's haloscopes, nuclear recoil experiments, NMR experiments, GPS experiments, and so much more. But I want to make the case that precision experiments, which are often AMO experiments, should be included in the big list of dark matter direct detection experiments. So I'm arguing this because the field of precision measurement is in an amazing period of progress, which Eric likens to Moore's law. And it's really true. You already saw how the electron Idiom has moved a factor of 100 in less than 10 years. We see similarly amazing progress with things like atomic clocks. There's plenty of other incredible measurements like this out there, and a lot of them are so sensitive now that they can really put a huge dent in the parameter space in the search for dark matter. This is exciting, and I really think that this is something that we as a field should take advantage of. So now let's assume that we do. This brings up a really important question, which I think Eric put really well. He said, at the threshold of this era, we should not be asking how is the analysis of hypothesis exclusion typically done, but rather, how can we get the analysis of hypothesis exclusion right? So let's talk about trying to get it right. When we first started this project, it was not clear to me at all. My first step was really obvious. I looked up what people have been doing and I read some books and papers. One of the first things that we noticed almost immediately is that none of these methods had a particularly appealing way of dealing with the look elsewhere effect. After doing a bunch more digging and a lot more struggling, we also realized that none of these methods had a way of dealing with the stochastic nature of the dark matter field, the scale of the stochasticity changing as your measurement time approaches the dark matter coherence time, the differential sensitivity of different measurement quadratures, and even the finite sample time for fast hypothesized oscillations. So note, I will be discussing stuff like the look elsewhere effect and the stochasticity of the field in more detail later. So if you haven't heard of those things, don't worry, hang on and we'll get there. So We found these issues and we were trying to find a solution using the usual frequentist threshold-based methods. And it was a huge struggle, honestly, not my strength. But luckily, a colleague of mine from JILA named Dan Palkin had been working on a haloscope dark matter search, and he had developed a Bayesian framework for performing hypothesis exclusion, which had already solved the look elsewhere effect problem. We quickly realized his framework was much better suited to solve our remaining issues. So with his help, we were able to extend his framework to our analysis and to solve the rest of the tricky problems, which to date, no one had solved. So I'm actually going to harp on this last part a little bit, because in my opinion, it really is the difference between getting it wrong and getting it at least closer to right. If you fail to address these issues, your exclusion will be too stringent. Gary Centers and co. wrote a lovely paper where they showed that failing to address the stochasticity issue alone means that 7 currently published exclusions are too stringent, and some of them by about a factor of 10. So these issues really aren't just small things that you can ignore. If you want to get these right, you have to address them in your exclusion. But have no fear, I have suffered so that you don't have to. So I'm going to spend the rest of this talk giving you an easy 10-step program for this analysis framework. And with minimal pain, you too can become a dark matter experimentalist. Okay, so let's get started with the recipe. The initial steps are the easiest, at least for the experimentalists. So step 1 is accost a few theorists until they tell you what kind of dark matter you're sensitive to. Because we know virtually nothing about the microscopic nature of dark matter, there's tons of possibilities out there, and your system could be sensitive to more than one. So good for you. Step 2, collect a bunch of data in your main experiment, which hopefully you're going to do anyways. And step 3 is to get good timestamps for each measurement you made. So this actually initially caused us quite a few headaches because we hadn't really thought about this when we took our data. So we had to do some forensics to ensure the timestamps we did have were up to snuff. In the next generation of our measurement, we actually installed a GPS clock, which gets triggered every time we take a measurement. So now we have a very precise timestamp saved alongside each measurement. I definitely recommend this if you're embarking on this anew, but if you have old data that you haven't done this with, your computer's timestamps will probably be good enough. I would definitely recommend that you check right now that you are using a NIST time service or something similar and not the Windows time service, because that will hurt you. So now you have a time stream of data, and assuming you're looking for an AC signal, you need to figure out which frequencies you're interested in. This is also a super easy step. So you just set your slowest oscillation frequency to 1 over the inverse time span of your data set. So this means you expect to see about a wiggle in the whole time you're observing. Your fastest oscillation is just the Nyquist limit for the speed at which you are taking data. So in our case, each data point that you're looking at here took about 22 minutes. So that works out to about 380 microhertz. So we were actually able to extend our analysis over an additional 3 orders of magnitude by breaking each of these points apart into its component parts, which took about a second to take. So our actual highest frequency is about ½ a hertz. This is a nice trick, but I think it's probably pretty boring for a talk like this. But if you're interested, I'll be happy to explain it later. Now, if you're really thirsty for more parameter space, you can extend your analysis in both directions. So you can go for lower frequencies, of course. You can check for ½ a wiggle. And on the higher end, you're technically kind of stuck unless your data is unevenly sampled in time. So in that case, the Nyquist limit ends up being higher than if the data was evenly sampled in time. Here's a little reference if you're unfamiliar with that. Of course, almost every single real physics experiment is going to have unevenly sampled data. So this totally works in your favor. So now you have a window of frequencies to look at, and you need to figure out how many frequencies to check inside that window. Usually the dark matter will be much narrower than your spectral line width, but that's okay. Your spectral resolution is about 1 over the inverse time span of your data set. You want to sample more finely than this so that you don't miss anything, but your samples will actually be evenly spaced over several decades. So you don't want to go too crazy and cost yourself too much time. We settled on 1/6 of our spectral resolution. Okay, now you have a time stream of data and a set of frequencies you want to check for oscillations. We're already halfway through the 10-step program. Now you basically want to do a Fourier transform. I put Fourier transform in quotes because you can't do that with unevenly spaced data. But luckily, astronomers solved this problem years ago, and those solutions super simple. It's called least squares spectral analysis, or sometimes you'll see something called a Lom-Scargill periodogram. It's just a least squares fit of your data to a sinusoid. So all you have to do is minimize this quantity, chi-squared, over A and B at each frequency that you've already selected, new, of interest. So each point here is a yi, it has an uncertainty sigma I, and it was taken at a real world time ti. So the really nice thing is that this is analytically solvable. Because you have selected new, this is a closed form expression. So you actually don't need to do any fitting of your data. You just need to plug it all in and solve. Okay, so once you do this, you'll have best fit values that here I'm calling A naught and B naught at each frequency of interest. So the result looks something like a power spectral density. In this case, it's a measured oscillation amplitude. So here's the result for our search. We see, for example, spikes all over the place. And now what we need to know is if any of these spikes are just noise or if they're real evidence of dark matter. So to put that more precisely, what we want to ask is, what is the probability that any of these peaks correspond to a real dark matter signal instead of noise? Okay, so the first step in answering this question is to answer, what does noise look like? So we did this by simulation. It's pretty easy. We just simulate data, which by construction has no oscillations in it. We run it through our least squares algorithm to get values of A and B. And then we repeat this until we have a distribution of A and B at each frequency of interest. So with this distribution, you can already say what the probability is for measuring each value on the previous slide if it was just coming from noise. So depending what your system is like, simulating data which does not oscillate, but which faithfully replicates your real data's actual noise and structure can be really hard. This can be the hardest step for the experimentalist doing this. In our case, it was almost impossible, especially for the portion where we broke each EDM measurement into its component parts. But in the end, I realized that you can actually just shuffle the timestamps of your data. This is a beautiful way of keeping all the spectral features of your real data while deliberately erasing any coherent oscillation. I would definitely recommend this. Okay, so the next step, obviously optional, but I would recommend that you blind your result by doing all the following analysis on one of your fake data sets that you just generated before you run it on your real data set. I think of this as good experimental hygiene. Okay, so now you know at each frequency of interest, the probability distribution of your noise and what your actual measured oscillation amplitude was. To complete the picture, you need to figure out the probability distribution for the dark matter signal. So to do this, we need to take a little step back and think about what we're actually looking for. So ALPs are called ultralight, which means their mass ranges from about 10 to the minus 24 to 10 to the 1 electron volts. But the actual local dark matter density is high enough that we need a lot of particles to make up the density we observe. So this means that they must be bosons. If they were fermions, the Fermi velocity would exceed the galactic escape velocity. So they're bosons, and we end up with a bosonic field with high mode occupation oscillating at the Compton frequency. So like Eric says, we basically have a Bose condensate at finite temperature, so it's fluctuating, and that means that there's a velocity distribution. Astronomers have measured that distribution, and we know that for our Earthbound labs, we have a coherence time of about 10 to the 6 cycles. 10 to the 6 is a fairly high Q oscillator, and this gives us a lot of experimental power, but it is still finite, and so it's something that we need to be careful about. So the finite line width means that we have a stochastic field, and it matters what time scale you take your measurement over. So I took this figure from Gary Center's paper, which lays out the whole situation quite nicely, and I definitely recommend you read it if you're doing your own dark matter search. The vertical axis is the normalized dark matter field amplitude, and the horizontal axis is time normalized by the coherence time. So if your measurement time significantly exceeds the coherence time, then your null result can very safely be interpreted as a constraint given the average local dark matter field amplitude. But if your measurement time is less than the coherence time, you're probably going to take a single sample of the stochastic field amplitude, and then it would be totally incorrect to assume any given fixed value. So for example, you could, by bad luck, be sitting near a null in the field like here, in which case your exclusion should be much less stringent than if you're sitting near a maximum like here. So you have to run through these numbers. Here's a quick run through of the numbers for our experiment. So our total observation time at low frequencies is 1.5 years. Our minimum frequency is 27 nanohertz. So 10 to the 6 cycles takes over 1 million years. So we're in the case where our observation time is much less than the coherence time, and we are going to take a single sample of the field. At higher frequencies, we were observing for about 11 days. Maximum frequency is 400 millihertz, and 10 to the 6 cycles is about 29 days. So we're actually approaching the coherence time. So in this case, now we expect to see decoherence of the field affecting our measured signal amplitude. So it's going to be like a attenuation. Okay, so now we've laid out the basic parameters to determine what an ALP field should look like. So a single mode of the ALP field looks like this. It's an oscillating thing, and the amplitude is a Rayleigh distributed random variable. The prefactors are the mean local dark matter density and the mass of the ALP. So the thing that oscillates with the ALP field with some coupling. So P2 are some prefactors that you don't need to worry about. And this quantity I've highlighted in red is the hypothesized new physics coupling that we're going to constrain. So it's really easy. You can just break this expression apart into the quadrature amplitudes, which look like this. So these are the A and B that we constrain with our least squares spectral analysis. And because alpha is Rayleigh distributed, that means that both of these are Gaussian distributed. So I can tell you that the variance in each quadrature just goes like this. So we already have a noise distribution and it's Gaussian. And we know that a real measurement of the ALP signal will have noise in it as well. But because both distributions are Gaussian, this becomes super easy. You just have to add the variances, and then you have the distribution for measured ALP signal. So when we add the variances, we have A and B from our noise distribution and sigma x for our like ALP only distribution. And then what I've done is I put this factor psi here, which is going to capture all the sources of attenuation. So this is a very general attenuation factor. It's frequency dependent because you're going to get one of these variances at each frequency that you're checking. So you're going to have a psi at each frequency that you're checking. And this is how we'll use it. This is what we will use to account for things like the stochasticity of the field. So we have our dark matter distribution. It's Gaussian and it has these variances. So I want to just pause for another moment to talk about this attenuation factor psi. There's 3 major sources of attenuation that we've considered in our analysis, and it's possible that there are more that we've missed, or it's possible that your analysis has different ones. But the beauty is that you can just fold anything that you can think of into the attenuation factor psi. So in our analysis, there's 3 sources of attenuation. The first is when the observation time is less than the coherence time. You could be sitting in a null of the field. The second is when the observation time approaches the coherence time. Decoherence will decrease the measured signal amplitude. And then another one we found was when the observation time for a single Ramsey free evolution period is not small compared to the like ALP oscillation period, then you're effectively averaging over some portion of the ALP sine wave, which will lead to attenuation of the signal. So the details of how we account for each is probably too boring for a talk like this. I don't really have like the distance from the material to tell, but I have slides about it. So if you guys want to hear more about it, please feel free to ask. The point that I'd like to make is that with this setup, it's really easy to take into account these things that I really don't think should be ignored. You just put them in your like frequency dependent attenuation factor and you're all set. Okay. So now, at this point, at each frequency of measurement, we know what we actually measured. That's A naught and B naught. We know the probability distribution for measuring noise at each frequency, and we know the probability distributions for measuring an ALP at each frequency and coupling of interest. So here's where we're going to do some gentle statistics, and in a few slides, you will have the final result. So for this step, you just take the ratio of your noise and ALP probability distributions evaluated at your actual measured values for each frequency and coupling that you're interested in. So I've sketched a cartoon version of that here. The big red dot is like your imaginary measured value, and these are the distributions for the noise and the ALP. So I think this is a really intuitive step. All you're doing is comparing probabilities. The part that makes this Bayesian is just a name. So we've named this number the prior update, which means that we are going to update our prior belief to our posterior belief using this number. So it's not actually Bayesian yet. The next step will be Bayesian, but right now you're just comparing probabilities. So for example, if the update is 1, that means I had an equal probability of being in each distribution, and we've basically learned nothing. If the update is large, that means I had a higher probability of being in the ALP distribution. And that means that I think, oh, okay, I've increased my belief in an ALP at this frequency and coupling. And conversely, if the update is small, that means you were more likely to be sitting in the noise distribution. You've decreased your belief in an ALP at that frequency of coupling. I just want to note that so far we have conserved all of the information, which is a nice feature of this analysis framework. When you compare this to threshold-based frequentist frameworks, where you just say, was I below or above a certain level? That's really nice. Okay, so now you get this prior update, U, and you have it at every frequency and coupling of interest. You can plot it in a 2D grid. So with a little bit of averaging, here's what our result looks like. The horizontal axis is frequency, and the vertical axis is the coupling normalized by the axion mass. So the dark parts are where our measurement had a higher probability of being in the ALP distribution than in the noise distribution. So far we haven't done anything Bayesian except for naming this the prior update, but the next step is Bayesian. And this is where we'll account for the look elsewhere effect. But I want to take a quick detour to talk about the look elsewhere effect in case you've never heard of such a thing. So the look elsewhere effect just describes the statistical notion that if you do a given experiment enough times, at some point you'll get a seemingly unlikely result. So for example, if you flip a coin 10 times in a row, and then you do that 1,000 times, a few of those times you're going to see something like all heads. Or when you're searching a large parameter space, like in our case where we're searching over 1 million frequencies, you're bound to see a statistical fluctuation. So maybe this is. This is a super important issue when you're doing searches like these. You need to figure out a way to know if your peaks are real or if they're just a statistical fluctuation. Typically, accounting for the look elsewhere effect means shifting from a notion of how locally unlikely an event is to how globally unlikely it is. In other words, what might be seemingly unlikely in a single frequency bin can ultimately be rather benign when you consider that we're searching over 1 million bins. So just a numerical example is that if an event has like a 0.001% chance of occurring locally, it will occur globally approximately once if you look in 1,000 bins. So hopefully you can see that this is important and it needs to be accounted for. But unfortunately, it's still a bit of a thorny issue in the literature as far as I can tell. I haven't seen any broadly agreed upon method for accounting for it. Okay, so when you're accounting for the look elsewhere effect, it's important to distinguish between reporting exclusion and discovery. A lot of the dark matter exclusion literature has taken its cues from particle physics, which is reasonable on its face because those folks really are the experts at detecting new stuff. That's why we have all heard of a 5 sigma threshold, and that is a totally reasonable threshold in a rare event search. Note that this is a 5 sigma global threshold, not a local one. But particle physics analysis is different from our current needs in 2 important respects. First, it's geared towards discovery, and second, the parameter spaces searched aren't usually as large. So while it can be helpful to look to those experts, it's not like really wise to just copy what they're doing. Unless something really amazing happens, the vast majority of dark matter detection papers will be reporting exclusion and not discovery. So because of the look elsewhere effect, the coupling excluded should be scaled back as more independent hypotheses are interrogated. And just to put it like, again, in case you need a little bit of help, or in case it took you as long to understand as it took me, which was like months, it's because it gets really difficult to rule out any particular frequency when there can be imposter spikes hiding among them. And then because this is true for every frequency interrogated, your whole exclusion becomes weaker. So to deal with the look elsewhere effect with respect to exclusion, you need to answer the question as a Bayesian, what is the fractional change in my belief that dark matter of a given coupling exists anywhere in my full analysis range. So this accounts simply for the fact that your analysis range may be broad or narrow, and it is in a Bayesian sense a very reasonable question to ask. So on the next slide, I'll show you how to do it, and given what you've already seen, you might have a guess. So here's the big finale, the exclusion. To answer what your fractional change in belief in the existence of dark matter at a given coupling in your full analysis range, you take a modified ratio or prior update. So instead of going frequency by frequency and coupling by coupling, you now basically aggregate or sum the posterior belief over the prior belief. When you're done this, you'll get a number as a function of coupling. Now you want to find where that number drops below 0.05, and that corresponds to a 95% exclusion. So I'd like to point out two things. The first is that if this bump here was higher, like if it was 1,000, then we would probably be reporting discovery instead of exclusion. And I'd like to also point out that we've set our priors or prior belief to be logarithmically uniform. But for an actual log uniform distribution, there would be a constant both in the numerator and the denominator, but you can see really easily that that would just drop out. Okay, so we can plot the same exclusion on our heat map from previous slides. The dashed line shows the result for the entire analysis range, while the blue lines show the result for each decade separately. So here's the rub. Some people are uncomfortable with Bayesian statistics because it has a prior belief which they think is subjective. I completely understand this sentiment. I used to be an avowed frequentist myself. It wasn't until I was doing this analysis that it became clear how superior the Bayesian approach is, in my opinion. But to ease your mind, I'd like to point out three things. The first is that our analysis is largely independent of the priors. The prior update, which is shown here as the grayscale map, is completely independent of the priors, and we've made this matrix available to anyone who wants to explore it however they want. Our exclusion also does not even depend on the absolute scale of the priors because the constant dropped out. It only depends on the profile of the priors. But the profile is important, which I'll get to. So the second point is that choosing a log uniform profile is absolutely the reasonable choice. There's lots of reasons for this. The first is that the masses of known standard model particles are distributed over many decades, so there's no particular reason to expect new physics to be any different. The additional one is that the body of literature surrounding this type of dark matter has only constrained it to exist within 25 orders of magnitude in mass. And that means that we have actually already implicitly agreed as a community on logarithmically uniform priors. So the third point is that the choice of priors is isomorphic to the choice of power thresholds set for detection used in frequentist analyses. So you'll often read about a 95% confidence interval for each frequency examined. All of the published frequentist analyses of this type that I've seen use a constant threshold for detection over a large frequency range, which is silly. That's because it's equivalent to choosing uniform priors over several mass decades, which amounts to only doing your search in the highest decade. Like you're saying that there's a 10 to the 6th time higher probability that the ALP exists in this decade than this decade. And if that's what you really believe, then why are you even doing your searches in the lower decades? So you can solve this with a frequentist analysis by choosing a frequency-dependent threshold, but then you've done something which is isomorphic to choosing a profile of the priors, so then you're being just as subjective as a Bayesian. So I really think that it is a meaningful practical advantage, both as the scientist doing the analysis and as the scientists who are absorbing and critically examining these results, to have clearly stated priors and justifications for them, because it makes your assumptions explicit. When you compare this to a frequentist analysis, the assumptions can be hidden, unexamined, and sometimes indefensible. Okay, here we are, we've done it. So ultimately, you'll plot your exclusion with other existing ones. So we are the first laboratory exclusion over 2 mass decades, which is nothing to sneeze at. And as far as I know, we're the only group that's done this exclusion, accounting for all the subtle effects like the stochasticity of the field correctly. Gary Center's paper actually points out that this exclusion is probably about an order of magnitude too stringent because they forgot to account for the stochasticity of the field. So I'm hoping that our result can serve as a template for what I expect to be a slew of results coming from precision measurement groups over the next few years, so that those folks can just stay focused on their beautiful measurements and not have to worry about all the nitpicky stuff that we worried about for you. Okay, so that's how you do dark matter analysis from a time stream of data. If you found this overwhelming or confusing, I'll leave you with just one thing I want you to take away from my talk, and that is that no lives matter until Black lives matter. So thank you. That brings us to the end of the talk. Thank you all so much for coming. I would be remiss if I didn't thank everyone who helped make this analysis happen. I want to give extra special thanks to Dan, who taught us his analysis framework, and Ben, who was like our local quasi-theorist who made all the dark matter specific stuff way easier on me. It really would have been horrible without them. Thank you all so much.
Wow, thanks for this spectacular talk. It's I don't know, it's probably, it can't be overstated how relevant it is for the stuff that here in Mainz, right? I mean, all the discussions that you like solved there in front of us is just some discussions that we went into in detail into and were arguing over all the time. So it was super important and great to have you here. Thanks. Are there questions?
Yes, can I ask a question, or like I don't see the...
Yeah, please. Oh, there people start raising hands. I apologize. I didn't see that, Dima.
So I guess was Dima first, so who should he go first, or?
Oh, no, go ahead, Alexei.
Okay, all right. Yeah, I actually have a question about kind of the beginning of the talk. Well, first of all, thanks for the excellent talk. I mean, it was really great to hear. Thanks. So that's the first thing. And I just had a question at the very beginning, and that is like when in your first slides when you mentioned sort of the the relation between the basically the EDM value and the basically the energy of symmetry breaking, close to the very beginning. Yeah, exactly here. Could you comment on this, please, a bit, because I'm not really knowledgeable about this. So could you kind of explain a bit more, like if the EDM value is some value, suppose you set it, suppose you discover it, suppose you measure it to be non-zero, what would that mean? If you could explain in more detail. Thanks a lot.
Okay, yeah, I'm going to try my best. I'm not a high energy theorist, so please pardon me if I get this wrong, but the general understanding is that it depends on which new physics theory you're talking about. And they all have the symmetry breaking in different places at different amounts. So you don't necessarily have to put all the CP violation into something like an electron EDM or into the, what they call that, like the lepton sector. You can put that somewhere else if you want. So when we say that this constrains symmetry violating at 30 tera electron volt level, that's probably because they put all the symmetry breaking in the lepton sector. So it's like the strongest possible statement you could make about symmetry breaking. I'm sure there's other new physics theories that don't have such an impressive level of symmetry breaking that this experiment disproved. But basically, the new physics theories, there's a very famous theorist who basically said we need CP violation and we need quite a lot of it to explain that there's matter in the universe. And so that's why most new physics theories are actually sitting right around here, like what is it, almost about 10 orders of magnitude more CP violation than the standard model has, because they just need it apparently to explain why there's matter in the universe. I'm not sure if I answered your question.
Yeah, I mean, kind of. I mean, just to make it more sort of specific, just suppose, right? Just suppose that you do an experiment and you do measure that it's like 10 to the minus 30. Okay, suppose that you discover it, okay?
Right.
What would that mean? Could you explain like sort of your next steps?
Oh, I see. So that would mean that we throw out the standard model, goodbye, and we start to try and sort out which of the new models describes our universe best. So it would be huge in the sense that we'd throw out this darling of modern physics, and we take something like supersymmetry on as our new model for physics. Now, each of these new models has other predictions that are totally different. So they would predict new particles or maybe like new forces or something crazy. So then we'd start searching for those new particles and new forces. And that would like open up entire fields of physics searching for these kind of weird particles that we've never thought of, that would match the kind of little slew of models that would be right in the range where we discovered in EDM. Does that make sense?
Yeah, definitely. Thanks. Thanks a lot. Yeah, that does. Thanks.
Well, Dima, now it's you. Sorry for ignoring you before.
Yeah, actually, in the middle of the talk, I sent Tanya an email saying, Tanya, very rarely I agree with everything that the speaker says, and so far I agree with everything you say. That I no longer can say that, because, for instance, you just said you were going to throw the standard model away. We're not going to throw nothing away. That's not how physics works, right? When we got relativity, we didn't throw Newtonian mechanics away. It's a cherished, heritage. We don't destroy it. We keep it, and this part of our physics, it just has its own domain. I think. Okay. The other thing is about your passionate propaganda of the Bayesian approach. Yeah, I think any approach has room if it is reasonable. And I think there are, as you pointed out correctly, and I fully agree with this, that there are different questions that you can ask. And for instance, if you have done this broad search and you ask yourself, have I discovered anything or not? And this is a very, very important question. And then you need this global analysis. But then tomorrow, I'll call you on the phone and I say, Tanya, we are seeing some interesting peak that could be dark matter, and it is at this particular frequency. And then what you'll have to do is you'll have to go back and yeah. So that's a different question, but the data should be used for answering all kinds of questions like this.
Yeah, absolutely. Most good dark matter searches have the ability to do a rescan. In other words, if they do see a peak that seems convincing, they'll go back and double check, which is a good setup.
I have a couple of questions, actually, if I may. One is, have you looked at different couplings of the ALP, or probably two different couplings, right?
You're just like, this is electron coupling, right? That's the only coupling that you're putting exclusions on.
It's the gluon coupling, actually.
What?
Yeah, so there's 4 couplings that we're sensitive to, but a bunch of them scale with the mass. And because the mass that we're checking is like 10 to the minus 24 electron volts or 10 to the minus 22, it's like pointless. Like we basically don't have the sensitivity to 3 out of the 4 couplings. So we're only actually checking one of those.
Could you elaborate why you're sensitive? I mean, like, is it intuitively clear why you're sensitive to the gluon coupling? Or is this, could you elaborate?
Oh,
maybe?
why we're sensitive to the gluon coupling? I'll take a stab at it, but it's probably wrong. But the hafnium fluoride, basically the electron is seeing relativistic effects. And when it's swirling around in this polarized molecule, when it goes near the hafnium, which is a very heavy atom, it like kind of swoops down close to the nucleus, apparently. And so in its swooping, it sees like some nuclear effects.
But what you're looking for is like an electron EDM, right? So, and I don't know, maybe Dima can correct me if I'm wrong, but, or someone else, it's like, isn't that the electron coupling that induces electron EDMs in?
Yeah, you've discovered something that I swept under the rug. So I talked about the electron EDM search for the first third of the talk, but there's other things that have CP violation. And it turns out that the thing that has CP violation that the axion is sensitive to is not the electron EDM. So the electron couplings that we want to think of, we're basically just not sensitive to. So that's that CS parameter. And in the high energy field, they sometimes use both the constraint on the EDM and the CS parameter. They have like different slopes. So you can cross them together and get an even smaller like portion in the parameter space with our EDM measurements. So basically it's like saying, there actually is no EDM, but there's a big CS thing, and we're doing all our constraint based on this CS parameter. So sorry about that. I swept that under the rug, but as you can tell, I totally don't understand it.
So you are sensitive to a coupling that depends on the electric field, right?
Are we sensitive to that?
Okay. So for instance, the Edm experiment, it set limits on the Edm coupling, that's the gluons, and then also on the gradient coupling. So I'm wondering why you only set limits on only one.
On the alp-gluon coupling, yeah. So we only set limits on the alp-gluon coupling, and then there is the gradient coupling, which again scales like mass. And so that's because we're at such low mass, it's just too small. Like we don't have any meaningful sensitivity.
No. EDM sets limits on both in that range, and so you should be, I think, sensitive to that as well. And there's only difference in the analysis a little bit.
Okay. I mean, Dima, you said you have a couple of questions.
Another question I had was, so nowadays people think a lot about the polyatomic molecules, symmetric top molecules for the EDM searches. What about the trapped polyatomic molecules? Is it possible?
It's totally possible. It's more intuitive to think about a diatomic spinning in an electric field. But I don't see why a polar atomic couldn't work, because the polarized part is usually still a diatomic, and then there's something else that's dangling off the top, right? So it's totally possible. The downside is that you have to do all the spectroscopy yourself usually. So the Edm experiment, I think Eric conceived of it in maybe 2004. And the first result came out in 2017, which is a pretty rough timeline unless you are Eric Cornell. So we had to do all the spectroscopy ourselves, and we had to figure out how to do everything ourselves. I think it would be a lot faster if Eric decided to do a polar triatomic. It would be a lot faster because we could probably wrap the spectroscopy up in about 6 years. And then we have all the trapping technology and everything else developed. But that being said, he already has a different scheme for sensitivity that should get us a few more orders of magnitude. And it doesn't have anything to do with polar triatomics. It basically takes, like, the downside of trapped ions is you can only trap so many ions because they're all going to repel each other, and you're limited to your rep rate. So we have we measure for about 1.5 seconds right now. So our rep rate kind of sucks, and we can only count like maybe 1,000 ions. So we have like 1,000 ions every 2 seconds. It's not very good compared to the beam people who have like 10 to the 6 molecules per second. They're under the square root. Our coherence time isn't. That's why we're still tied with them. So Eric is going to combine a beam with a trapped ion. So he's going to basically line up a bunch of traps and have like kind of moving ion traps in a beam. So it'll be a lot closer to a beam experiment. It's basically like a hybrid ion trap beam experiment. We call it the bucket brigade. And that should get us down to like maybe 10 to the minus 31 and eventually 10 to the minus 32. So we'll be able to keep pace with the neutral people as they manage to trap their molecules, hopefully.
Cool, thanks. I actually have quite a few questions, but I will just drop them if nobody else has questions. So that's why I maybe start with a comment. So if you could go back to your exclusion plot. Because we had a long debate about this with Mr. Adelsberger and Will Terrano, and that is that I mean, I'm not sure whether you're interested in this, but you can have also exclusion power below the frequency that you give there, because otherwise it would just look like well, in your case, a neutron or a nuclear EDM, a constant nuclear EDM, if you have oscillations at lower frequencies than the one that you're sampling at, right? So if you don't observe anything, or if your observation is consistent with 0, that means that it's also unlikely that there is like a big oscillation going on. So you actually exclude also further to the left.
Yeah, that's a great point. Eric also realized that we have already experienced a bit of a battle with our Bayesian approach, like convincing people to go Bayesian. And so we could have gone a little bit higher and a little bit lower, but we kind of wanted to not ruffle any more feathers than we'd already ruffled. So that's why we sort of stuck with like pretty obvious limits on the upper and lower end, on the lower and upper end. Yeah. But that's a great point.
Cool. All right. Anyone else with questions? Well, I'm also not sure. I mean, like, I mean, you offered a couple of times that you will go into more detail. So I'm actually very interested in your experimental setup. And I have to be honest, I don't even know what you measure, right? Like what's the actual measurement, for example? Or
yeah, sure. So our actual measurement, we do Ramsey spectroscopy between two doublets. So it's something like this plot. So we have our molecule is either aligned with the electric field or anti-aligned. And then there's, because of the hyperfine splitting, well, sorry, hyperfines up here, our Zeeman sublevels. Like this, we measure the energy splitting between these two Zeeman sublevels and these two Zeeman sublevels. They're trapped ions and we detect them destructively. So we basically state selectively dissociate them and then we throw the hafniums that we get onto a screen. But luckily, because they're oppositely oriented in the field, so it's something like this, when they explode, one hafnium will go this way and the other hafnium will go this way. So we can simultaneously detect both of the doublets, which is really nice. Here's a little cartoon of that happening. We don't have perfect contrast between the two doublets, but basically we do Ramsey spectroscopy. So we create a superposition in both doublets and then let it evolve for some time and then project that superposition and measure a population difference. If we didn't figure out how to do this, we would be basically screwed right now. We have fractional noise in our experiment, and if we weren't doing differential detection, we would have literally, I don't know what we would have done. We'd be totally stalled. So figuring out how to image both doublets simultaneously was a huge advance for us.
cool, thanks. And I mean, how does the rest of the experimental sequence look like? I mean, what do you start with? And like I saw that you mentioned a couple of laser beams, but I forgot them all.
That's okay. Yeah, there's 14 lasers, and like as a grad student working in the lab, the majority of my time is spent kind of, it's like herding cats, you know, you're just wrangling all of them to work at the same time. But so we start with a neutral, we use 2 lasers to ionize it. Those decay into a different electronic state than what we want. We use microwaves to mix these electronic states, and then we transfer them. So that's, that's 5 lasers already. Oh, I forgot the ablation is another laser. We transfer those. So this is the ground electronic state. That's where we created our ions. We transfer them through an intermediate state into our Edm sensitive state. Then, because this is just like incoherent transfer, this is just decaying all over the place into different vibrational and rotational levels. We turn on a bunch of lasers to clean up the other vibrational levels that we don't want. The vibrational decay is about 100 milliseconds. So anything that lands up here will decay into our science state.
And why not stir up?
Oh yeah, we tried stir up. We just can't get the Rabi frequency we need. All of these wavelengths are something annoying that there isn't very good solid state technology for or something. So yeah, we tried. Then we pump. So now in this state, we are just distributed over the rotational levels. So we're distributed over hyperfine and Zeeman sublevels, but we need to start with a pure spin state. There's nothing we can do about hyperfine, but we at least use circularly polarized light to pump all of the population into a pure spin state. Once we have that, then we can do a pi/2 pulse and create a superposition. And then we can do a second pi/2 pulse after a certain amount of time. And again, we want to just deplete one of the spin states. So here's what the pumping looks like up close. I'm sure you all can you all understand, like MF pumping or whatever you want to call it. So we've created a pure spin state, say in this stretch state. Oh, this is a funny little animation. And then blah, 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 it evolves, and then we're going to deplete one of the spin states. And then we explode the molecules and state selectively detect the population in each doublet. So that makes a Ramsey fringe. The doublets go out of phase, and they go back into phase. And I guess like you saw with that Ramsey fringe earlier, we're totally anally retentive about how we take our fringes. We just take 4 points. We only take, or sorry, we take 8 points total, which is kind of amazing. We just take 4 points at the beginning and 4 points at the very end of a 1.5 seconds fringe. We know exactly what the frequency is that we just land right on the sides and the tops. We just average down a bunch on the sides because that's where all of our sensitivity is. Dima, you've got your hand raised?
Oh yeah, sorry. I was just like, I'm still digesting intellectually, but I think I'm done. At least it's more clear. So thanks. And yeah, Dima.
You mentioned this bucket brigade thing. So I understand why having many traps in parallel improves your sensitivity by square root of n. But I did not understand what you said about marching the molecules from one trap to another. Why does that help?
It's we don't want to have 100 separate traps. So it's basically a tube that has like a little potential. It's got AC trapping potentials in the what do you want to call it? The like axial direction along the tube. So there's basically a little trap that's actually physically moving down the tube, and there's another one right behind it, and there's another one right behind that. Does that make sense?
Now,
so
why
instead of
would you move them? Why just to basically them?
To give the free evolution time. So it's like a vacuum chamber with a tube and then another vacuum chamber. So you're going to prepare out a little packet of molecules, and then you need to get them out of your vacuum chamber so that you can prepare out a new packet of molecules, and you're going to send in all your lasers and so on to make like your little state. And then you're just going to send them in a tube to move along at whatever speed you choose so that they can evolve for however long you want them to.
Okay, so the preparation and detection are in the first chamber, and in the other one, and the tube is just the free evolution time, right?
Exactly. Yeah.
Because you're also gonna gain with that V cross E effects. You know.
Yeah. It's going to be really hard. I'll be gone by then. They also have a new molecule, and it's in the ground state. The Edm sensitive state is the ground state. So unlike us, where we have all of this business getting into the excited state and then cleaning things up, they're just going to make their molecules down here. So they'll have much simpler state prep. And that also gives them a much longer lifetime. We only have about 3 seconds here. They have, infinite up to things like thermal effects, like black body radiation. So they're going to aim for 30 seconds. So they'll get like another order of magnitude in coherence time just by changing molecules.
Cool, thanks a lot. I mean, I don't have a question, but maybe since you're timestamping data, you should totally be included in the GNOME network. But what do you think, Dima?
Yes, of course. Everybody should be included in the global dark matter search network and cross-correlating their experiments. Absolutely.
I mean, like you have super sensitive data. It's timestamped. We should totally cross-correlate it with something that either we have or someone else has. And you should also be looking for topological stuff, right? I mean, Joey is still on the call here. I don't know, but he's one of our graduate students together with Hector, who are spearheading our analysis of the global network of optical magnetometers to search for exotic physics. And that is, we're looking for domain walls, basically. So dark matter that is hitting Earth, and that would be visible. I mean, I actually think in your data, in your raw data, I saw a domain wall crossing in like something like 2 years ago. and would just be nice. Yeah, there it is. There it is, clearly visible. Oh, no, there it's not.
Oh, is it here?
Basically, well, basically just
Here.
to what Arnie says, it's not looking for an oscillating signal, but a transient.
Yeah.
So it's yeah.
And if you have transients, you cannot average, and you have no look elsewhere chances and whatever. But I mean, not that look elsewhere as a chance, so that was wrongly. You need other sensors that are sensitive to your dark matter candidate that also feature such a topological thing. So yeah, I mean, we are not at the beginning of it. We are at the not even at the beginning of the analysis. It just takes. I mean, you have experienced, I believe, a fair bit of annoying analysis of data in your time now. So we are struggling through that too. And with like those like temporal features, it's even more annoying, right? So to place any kind of exclusions on that. But maybe, I mean, you have a sensitive detector, so we should totally start discussing including you.
Yeah, I mean, why not, right? Like, that's a super cool idea. And because we're finally GPS locked with our timestamps, it would make sense.
I like sorry, but we have another thing that we are also interested in, and that's even newer, and that is correlating precision experiments with observations, astronomical observations, right? So, for example, with gravitational waves, those are, if you want, also topological things that hit Earth at a given time due to some cataclysmic event in the universe somewhere. And I mean, we know nothing about dark matter, but it can be feasible that at those energy scales, that's the merger of a binary black hole or something like this, that you go through a resonant production of dark matter too. That is an ultra-red, and that can be correlated with, I mean, you have the observation, you have the gravitational waves that hit Earth and we detect it, and then you take your experiment and look whether you observe some spike or something related to this. We need theories to create models to exclude something, but I think it's very cool and sort of new direction that we're going here.
That's amazing. Yeah, we're right on this threshold of trying to figure out what the heck is going on with dark matter, and it's an exciting time to be a physicist. It feels like there's so much to do.
Yeah. Cool. Are there any other questions? Yeah, doesn't seem to be the case, so I think we can close the seminar here. Maybe I advertise for last time. The next seminar going to be given by Hatice Aytuk about something completely different. So it will be more quantum. I mean, this was very quantum. Actually, very interesting application of quantum mechanics, and the next one will probably be a different non-fundamental physics application. But yeah, thanks a lot for coming. It was a really nice talk, and hope to see you soon in real life somewhere. Thank
you so much.
Thanks, Tanya. Bye.
Bye.
Goodbye.